First of all, before I start, let me also thank the organizing committee for setting this nice conference. And yeah, my name is Theodoros, and I'm a PhD student in Heidelberg University. I work with neutron star mergers, and my PhD advisor is Andreas Bauswein. So today I'm going to talk about, let's say, neutron star mergers in general, and hopefully at the end I will have some time to talk about a way to parameterize the gravitational waves we get from such events. Okay, so before I start, let me just say a few words about the equation of state. So why do we study these neutron star mergers? So the goal, of course, is to learn more about the physics inside the neutron stars. And so far, we have a nice understanding of it, but our knowledge is not complete. So there is a density regime where we make some speculations. And for that, neutron star mergers are a good way to study this system, this problem, because when the two stars merge, we reach very high densities, and then we also get gravitational waves. And these gravitational waves, their properties depend on the equation of state. And yeah, basically this is what the plot here I have on the right is basically the mass and the radius relation for single stars that do not rotate. And its curve corresponds to another model, okay? So the goal is to constrain this plot, let's say. So generally, when we talk about neutron star mergers, we have two large categories. Of course, as Professor Kokotas talked in the first talk, today, the picture is very complicated, but we can define at least two simple categories. One of them is when the total binary mass exceeds some specific value, some limit. In this case, when the two stars merge and they collide, they immediately form a black hole. Okay, and the other case is that the total mass is below that limit, below this threshold mass. Then we end up with neutron stars, which rotate very rapidly. They are very much deformed and oscillate in many different ways. And the interesting thing is that these waves result to gravitational wave emission. Okay, and we can learn about the equation of state from these events. But before I move forward on the post-merger phase and the gravitational emission, I just want to mention this. So even this limit, this threshold mass for black hole formation, carries information for the equation of state. And here on the left, I show a figure from this recent work from the group and the collaborators, and where we calculated this threshold mass for a sample of equation of state. And then we compare and express these values with respect to stellar parameters, like the radius of the 1.6 solar mass star for different equations of state, and the maximum mass allowed in this case, and in these models. And what you see is that all these values lie very well in this plane here. So there is some systematic trend and something that dictates this value, and that depends on the equation of state. So every part of it, every part of these categories gives some information. That was my point. So, but yeah, for the rest of this talk, I will talk about gravitational waves we get in this post-merger phase, in the remnant that oscillates. And yeah, thanks to the previous talks, I don't need to spend a lot of time here, but I just want to mention that we have two phases. One of them is called the in-spiral. It is where the two stars orbit around each other, they emit gravitational waves, and eventually they merge. And the rest is this post-merger phase, when we talk about the remnant star that oscillates. Okay, both of these regions give us information about the equation of state. But as I said, I will focus on the post-merger phase. So I have a movie, but unfortunately Google Slides do not allow me to play it very well. I will try to open another tab, but so do you still see the presentation or the tab or with the movie? Okay, I'm not sure. Wait a second. Sorry for that. Okay. So hopefully now you see some movie. So basically this is how a Newton star merger looks like. We have the in-spiral phase, we have the tidal deformation of the stars, and then we end up with a remnant. Okay. Now if I could go back to the presentation, it would be good. Sorry. Okay, so hopefully now you see again the presentation. So this is just a snapshot. This is the resonance density of the preview snapshot of the movie. This is the resonance density of such a system. So this is the newly formed remnant, let's say. So it's just a few milliseconds after the collision. And what is clear is that this system is very much different from a spherical star. It has this bar shape that already gives you some quadruple deformation. And if you think about it, this should spin and also oscillate a lot. So this will emit gravitational waves. And in fact, this is what George was talking about. This is the F-peak mode. And this is the dominant component in the post-merger spectrum that we have. And this is what I saw on the left. It's a Fourier transform of such a gravitational wave. X-axis is the frequency and Y is the amplitude. And you can see a very well-defined, let's say, strong frequency peak. And this is associated to that mode. And this is important because this value depends on the equation of state. Okay, so for example, for a system with a similar mass, a soft equation of state would result to a very compact remnant, and this frequency would have been much higher. And what I show here on the right is, let's say, the same thing in other words. So here we saw a correlation between this frequency, for example, of equation of state and different binary masses, and something like the average density of the star after the remnant. It's a bit more complicated, but let's say that for now. So here we have a series of simulations. We calculate these frequencies for different masses, and then we compare with the density. And we see this nice universal relation. Okay, this is very interesting because it can give us information about the density regime of the merger just by observing gravitational waves. Okay, so now I will try to briefly mention, I'll give you some information about two secondary components in the power spectra. But of course, I invite you to read the original papers by Sterioulas and Bauswein and their collaborators, 2011 and 15, where they introduced these concepts. I will not show the movie because it will not work, but one of the components has to do with the fact that when we have a newly formed remnant, we end up with some bulges on the faces of the remnant. These are formed during the tidal deformation of the two stars. And the interesting thing is that the two bulges, like on this side and this side, hopefully you see the cursor, maybe now a laser, this side and this side, they have some angular velocity, which is different than, smaller than the inner part of the remnant. These carry enough mass and they last for a few cycles, a few milliseconds. So basically they emit gravitational waves. And we can see that in the spectrum. Another secondary component is related to the fact that the remnant also oscillates radially. This is because when the two stars collide, this impact excites this radial oscillation. Here on the left, I just show the maximum density of the system as a function of time. And I just want to mention that these two peaks here correspond to these oscillations that are radial. And in fact, this contributes to a coupling between the main mode and this oscillation, and therefore generates two additional frequency components. Okay. Now, the next step, which is part of my projects in the PhD, is to further, let's say, understand these secondary components. And for that reason, we consider a mass sequence. So we perform a series of simulations, and at each time we increase the total binary mass. Then we identify these secondary components. Oh, sorry, I think I skipped a slide. Okay. And then compare the spectra. Okay. So what I show here is the low mass configurations of such a mass sequence. And the spectra, of course. So, of course, there is a lot of information here, but because I don't have enough time, I just want to mention this. So what we see, it is that in the low mass configurations, the F spiral peak, which is the yellow dashed line, is always the dominant secondary component. However, this is not the case in the high mass configurations. So the more mass we have in the system, the stronger this radial pulsation is excited. Okay, and this means that also the coupling is stronger, and therefore these secondary components are now comparable to F spiral. Okay, and one last thing is that we can also observe this oscillation if we look at the minimum lapse of the system. So for those who don't know, this corresponds to, let's say, the minimum value of the potential as a function of time. And from this plot, I only want to mention that the amplitude of this oscillation, which is due to the radial pulsation, is much larger. Okay, and yeah, so as I said, we do all of this because we will try to parameterize this post-merger signal. But why do we do that? So in order to make gravitational wave detections, we have to know how the solutions look like. And thanks to numerical relativity, we can do that for the post-merger phase. However, these models take quite some time these simulations take quite some time, and they're also computationally expensive. And what happens with detections is that LIGO and Virgo, for example, so they take measurements, and in order to find a signal, they use some solution, some example solution, and then they scan all over the data until they find a nice match. Of course, the actual process is much more sophisticated than this, but this is an example. And for this reason, in order to explore the parameter space, you need many waveforms. And also you need to be able to produce them quite fast in order to see if you have detections. And yeah, that is the motivation behind the construction of such a model. And actually this was firstly introduced by Weisbein and Sterjulas in 2015 and their collaborators, I think. And so where they introduced a simple model with these assumptions. So the post-merger should be simply a combination of 3 oscillation modes, 3 sinusoid functions. And the frequency of them are the F peak, the F spiral, and the F2 minus 0. And we can do that because these frequencies follow relatively tight empirical relations, especially the F peak is quite tight. So apart from that, we also consider some decay in these components. Of course, one has to explore this parameter space, and this is what I'm doing. But as an example, I want to show you this figure on the left here, which is basically a comparison between a simulation, which is the black curve, and the orange one, which is a model using this kind of analytic model. Okay, so you see a very nice match. And yeah, for the take-home message, I will keep it very simple, but the idea is that if we want to understand this post-merger signal, we have to understand how oscillation modes work in neutron stars. And in order to make detections, we need to have fast and accurate waveforms. And yeah, so far it seems that if one assumes exponentially decaying sinusoid functions, one can parameterize very well this signal. And yeah, this concludes my talk. Thank you.
Thank you, Theodoros, and thank you for being on time. Any questions for Theodoro? You can raise your hands, but also now you can unmute yourselves and ask.
One question I have, Theodoros.
Yeah.
Can you hear me?
Yes, yes.
Yes, so for the model that you showed in the previous slide, one before the last one, so does the model know everything about the equation of state or other information, or you just all this f-peak, t-peak that you have in the analytic description is just to model the simulation and you find them from the fit?
So let me think if I understand correctly the question. So the process is the following. We do a simulation with some equation of state that we know, right? And then in this particular case, we used the frequencies, the f-peak, f-spiral into -0 from the spectra. So you need some knowledge for the equation of state, right? So it's not a complete free parameter, but this is the case because maybe we didn't formulate a very sophisticated data analysis, method for that. So it is simpler, because we know the frequencies, we use them. But the other parameters. Yeah,
so let me reform the question. So take this model now and you do it in real observations. Will you extract any information for the equation of state or not?
Yeah, we haven't tried that yet, but I think there is a paper from Easter and al. From 2020 that they actually tried a very similar model. And I think they got some answer about how they can extract the f-peak. But we didn't do the full data analysis, but we work on that, yes.
Thanks.